The recording is live. Okay. Now I've just passed out 2 handouts to everyone. Number 1 is a colored printed copy of the periodic table. This will be the periodic table we will be referring to throughout the class. This is also the periodic table that will be provided to you as part of your exam booklet. You are, of course, free to write over this paper as much as you want. The PDF is on Canvas should you want to reprint. But again, you will get a blank copy with every exam, so you will not be allowed to carry in that annotated periodic table. Of course, recognize that we do have a periodic table on the wall over here. Now, we're not going to go through piece by piece, but there are some discrepancies between this periodic table and this one, mostly due to how they rounded decimals. I want to make it very clear. This is the one we will be using in our class. This is what I'll be using when making exams and making the keys, as well as any worksheets. The differences shouldn't be that significant. Like I said, it's just a rounding difference, right? And in some cases, this periodic table is slightly outdated. There are a few chemicals on it that are missing that were discovered in the last few years. This is the most up-to-date version of the National American Chemical Society's periodic table. Right. Please notice that it is in color. I do expect you to carry this to class on a regular basis, especially for the next few classes, because we will be making references to it quite a bit. Number 2 is a 4-page problem set. We've already been through this once before last week with measurements. Some of the questions we will do in class, some of them you will work on your own, then we'll review together, and some of them will be extra credit. They'll be applied towards the next exam. I'll tell you right now, actually, I'll decide when we're close to that so it's not confusing. All right. Before we begin, does anyone have any questions? All right. Very important reminder, tomorrow, Friday, is our very first wet lab. Number 1, you should have submitted the assumption of risk waiver form. If you're a minor, please turn that in to me, scan it and email it to me by the end of today. Please also complete the lab safety quiz. If you don't do either, one or both, you will not be permitted into the lab room and you'll have to take a 0 for that day. Well, you can do the quiz that same morning, but you'll be delayed when starting your set of the experiment. Number 2, since it is a wet lab, I do expect you to come dressed appropriately. That does mean, number 1, goggles. Hopefully everyone has secured a pair. If not, today's your last chance to do that. Feel free to send me a picture on Discord to confirm, is this okay with you or not? I'll quickly respond. I'm okay with friends in different sections. Maybe if you have a friend in the morning and you're in the afternoon, you switch goggles to save costs. That's fine with me. Otherwise, I expect you to be properly dressed. That means long pants, shoes, and socks, no open-toed slippers, no open-toed shoes or Crocs, no sleeveless shirts. I always recommend just carrying an extra change of clothes in your car on a regular basis. And of course, if the heat is a concern, you can purchase a lab coat and wear the lab coat, and that will take care of a lot of the coverage issues. If you are not dressed appropriately for a lab, I will send you home to change. Now, some of you may live within 10 minutes, so that's not a big deal. But for those of you who live like 45 minutes away, driving home means most likely missing the lab. And as a final reminder, my late time policy for a lab, if you are more than 15 minutes late without very good reason, you will not be permitted to enter the lab. And as a result, you'll have to miss that day's lab experiment, have to claim a 0. That's pretty much it for big announcements. I'd like to get started talking about the periodic table. All right. The periodic table's history is one of that is incredibly storied and up for a lot of debate. You see, something that we will find out over the course of today, something we will encounter over the course of the semester, is that oftentimes the periodic table, it isn't wrong, but it doesn't quite line up with our expectations. However, in the mid-1800s, a man by the name of Dmitri Mendeleev propositioned the very first version of the periodic table. He organized the elements in a table based on their mass and properties. In other words, he expected the lightest element would be the very first, and the heaviest element would be the last. This table that he proposed worked very, very well, although it wasn't perfect. In 1913, one of Dimitri's contemporaries, his name is Henry Moseley, he's actually the guy who coined that term that we know from last class, atomic number. We talked last class about how atomic number both refers to the number of protons as well as the number of electrons in a neutral atom. And with this term, we were then able to rank elements starting with Mendelev's idea, but implementing Moseley's idea. This eventually gave rise to the concept of periodicity, which is where the term periodic and periodic table comes from, where their observations allow them to categorize elements and their partners. And they observed a concept known as periodicity, where chemical and physical properties overlap in a periodic/predictable way. Chemical and physical properties overlap, or more specifically, share a pattern in a periodic way. Periodic or predictable way. So, with these concepts in hand, we can now look at what the periodic table looks like and how to interpret it. Is there anyone who right now does not have a copy of the periodic table? Raise your hand. You came in late. All handouts are available on Canvas as a PDF, usually within the same day. So if you did not grab a copy, again, if you need to reprint a copy, they're always on Canvas. All right. Everyone should have the periodic table in front of them. We're going to talk a little bit about how to interpret this, how to read this, things that we'll be able to broadly ignore for the most part, as well as things I want you to focus on. First and foremost, I want to get something out of the way. These two very bottom rows in red and green, I want to put this out right there. We will not strongly encounter this in Chem 300. These two bottom rows. One of the biggest reasons is, as I mentioned, the periodic table allows us to predict chemical properties, physical properties in a predictable way. The idea is that by organization, we're able to say, well, these two are close together, so they should be very similar. A lot of the exceptions occur in these two rows. So as a result, we don't really talk too much about them in this class. All right. Referring to the rest of the periodic table, I want you to notice two things, specifically the legend. Number one, right here just shows how the elements are organized and what the symbols mean. On the very top, we have the atomic number. Don't forget, what does the atomic number mean? It's the number of protons and the number of electrons. The symbol is a shorthand, typically 2 letters. We have the name right under it. And we have that average atomic mass, which, as you recall, is calculated from the isotopic abundance. So that's how to read the different symbols on this table. Please also notice the categorization shown here with the different colors. The first 4 are all classified as metals, just different categories of metals. Alkali metals, alkaline earth metals, transition metals, and other metals. I do not need you to be able to separately identify piece by piece, but I do need you to know there are metals on the periodic table. There are also non-metals, such as the halogens and noble gases. And they are considered metals, but metalloids may sometimes share properties with non-metals. So it's sometimes ranked in its own category. So what's the big takeaway I want you to know here? In the case of metals, they all share some characteristics in common. They're shiny, they're malleable, they're ductile, and most importantly, they're good conductors. What about, I'm sorry? Ductile means, well, malleable means bendable. Ductile has to do with, I believe it's how it can fit within certain shapes, like PVC pipes, be able to mold to a particular shape. Malleable refers to how easy it is to break down or be brittle. Question. Non-metals, expected to be the opposite. They're dull, they're brittle, and they're bad conductors. And finally, metalloids, they have overlapping characteristics, meaning that they have characteristics about have characteristics about metals and non-metals. So we just like to call them intermediates. Oftentimes when I refer to different elements in class, I'll say things like, we know magnesium solid, we know carbon gas, we know oxygen gas. You have to ask yourself, how does he know what's a metal, what's a gas? Refer to the color code, the legend. Over time, you'll be able to pick up the pattern, pick up the trends. The other thing I want you to notice is the labels. Here we have something called group and period. Group, or rather the group number, indicates the amount of valence electrons. This is a new term, valence. First time we've seen it in this class so far. It's kind of, I'm clearing up some space for myself. The term valence quite literally refers to outermost. As you can imagine, as we get more electrons, we get more shells. We liken them to the rings that orbit a planet. The rings are where these electrons are found. As we add electrons, we add shells, we add rings. However, we most often only care about the ones on the outermost shell. In other words, if an atom was a building and this building was multiple floors, all we'd really care about is what number is the highest floor. Why? Well, when elements react, it's only the outermost electrons that actually participate in reactions. They're our first line of defense. Following that building analogy, our top floor of the building is most important because in the event of an alien invasion, they're the first ones to go. So we care about that valence, that outermost electrons. The ones that aren't outermost are referred to as inner core. These are largely considered to be unreactive, aka inert. So what do groups specifically tell us? Well, as I just mentioned, they tell us the valence electrons. So let's take a second to be sure we know exactly what that means. On the periodic table, you should have noticed that there is a number floating above every column, above every group. It starts at number 1 and it goes all the way to number 18. Groups 1, 2, 3 to 12, 13, 14, 15, 16, 17, and 18. I did purposefully put that 3 to 12. I purposely did not break them up. The trend is straightforward. Group 1 has 1 valence electron. Group 2 has 2 valence electrons. Groups 3 to 12, they're the weird ones. They're called variable. They're weird for that. Group 13 has 3, group 14 has 4, group 15 has 5, 16, 6, 17, 7, 18, 8. You probably get the pattern. Now let's talk a little bit about that groups 3 to 12, that variability. Looking back on the periodic table, that's that blue block right there in the middle. Looking at your color scheme over here, these are what are known as transition metals. Transition metals have very particular behavior. They depend on the specific element. We talked about how earlier it was difficult to predict these guys down here, so we don't really talk about them. In a very similar way, it is difficult to describe transition metals, but we can still predict some behavior. All you need to know right now is that they exhibit a variable number of valence electrons. The other label, of course, are the rows, periods. Periods 1, 2, 3, 4. Just like groups tell us something about the atom, about the electron, what exactly do periods tell us? They indicate the number of rings. We talked a little bit about how we can liken an atom to a planetary being where there's this nucleus, the planet, and there are rings surrounding the planet, orbiting around it. It is on these rings that the electrons are found. They're consistently circling around the planet. As we add more electrons, we add more rings. The period number of periods, the period number tells us the number of rings to expect that orbit the nucleus. These are sometimes referred to as shells, these rings. This depends on who you're talking to. And of course, it should come as no surprise. If you're higher in periods, if your period number is higher, you are predicted to be a larger atom. Question always comes up about the periodic table. How much are we expected to memorize for the class? As a reminder, you will be given the periodic table as part of all of your exams. So I do not need you to memorize anything about it. You'll get a perfectly blank copy of this one, blank meaning none of my notes. What I need you to be able to do is understand, read, and apply the periodic table. That really comes back to understanding what the symbols look like and what they mean, as well as the numbers. It's very common to misread the periodic table, especially in an exam setting. So patience will be your biggest friend. Do you have any questions before I move on? The table. Valence electrons. VE stands for valence electrons. Okay. Let's talk a little bit about ion formation. Now, we talked about how the atomic number tells us the number of protons and electrons. We talked about how if we have an equal number of positive and an equal number of negative, the element is neutral. So by default on the periodic table, all elements are believed to be neutral, meaning an equal number of protons and electrons. These neutral atoms can either gain or lose electrons and upon doing so, they form what are known as ions. When we gain electrons, when a neutral atom gains electrons, this results in what's known as an anion, an overall negative molecule or atom. If we were started off neutral and we gained a negative particle, we overall end up negative. This is what's referred to as an anion. I remember it as a negative ion. If we lose electrons, to no one's surprise, we end up positive. This is what's referred to as a cation. So take, for example, one of the atoms we saw in last class, boron. Take a second to try to find boron on the periodic table. Its atomic number is 5, which means it's number 5 on the periodic table. It has a mass of approximately 10.81. As written, it is assumed to be neutral on the periodic table. It has 5 protons and 5 electrons. If it were to lose, if it were to lose an electron, meaning become B+, it would still have 5 protons, but instead it would have 4 electrons. Similarly, if it were to gain an electron, the number of protons remains the same, but the number of electrons changes. The key point I'm trying to make here is that only electrons can move. They're the first line of defense in a planetary system. They're the highest floor of a building. The number of protons remain the same because they will never move. So since now that we've acknowledged that atoms can gain or lose electrons, the question, of course, is why do elements gain or lose electrons? The simple answer is because of group 18. If we take a look at our periodic table, group 18 is over here on the far right. It's comprised of helium all the way to radon and oganesson. If we look at our labels, the purple, they're known as noble gases. Group 18 are noble gases. Noble gases are special, not just because they're called noble, but because in a lot of ways, they can be considered royalty. Why? They're known to be extremely stable. And that makes them the popular group. Everybody wants to be like group 18. They're royalty. They're very stable. But what is it about them that makes them so stable? Group 18 elements have 8 valence electrons. That 8 is what makes them so special. This leads to what's known as the octet rule. The octet rule explains the idea that elements want to resemble royalty. They want to resemble group 18. So they will do whatever needs to be done to have 8 valence electrons. This is what's known as the octet rule. There is only one exception to this, and that's helium. Helium has an atomic mass of 4 and an atomic number of 2. So it's a very second element on the periodic table. The simple reason why helium is an exception is because it actually only has 2 electrons in total. It doesn't even have the minimum 8 to be classified as an 8 valence electron atom. That doesn't matter though. Helium is still known to be a noble gas. It's known to be extremely stable. We use it at birthday parties for balloons and stuff. So the octet rule tells us ultimately that elements gain or lose electrons because they want to look like group 18. Group 18 has 8 valence electrons, but helium has 2. So 2 or 8 valence electrons is okay. Here's what that leads to. Redrawing that first table that we did. We're now going to add another row called ideal charge. I give everyone a second just to draw the table again. I need to get the periodic table once more at the ready. Okay. To understand what their ideal charge will be, I'd like everyone to look at their periodic table. Right now, for the very first example, we are going to focus on oxygen. It's group 16. It's the very first element. Now, oxygen, as written, has 6 valence electrons. How do we know it has 6 valence electrons? It's in group 16. Its closest noble gas is neon. And neon has 8 valence electrons. Technically speaking, it is also neighbors or, far neighbors with helium. But its closest noble gas neighbor is neon. Oxygen wants to look like neon in terms of its valence electron count. So what does oxygen need to do? Will it gain or will it lose electrons? It will gain. How many electrons specifically? 2 electrons. If you gain 2 valence electrons, that means you're overall going to be -2. So group 16's ideal charge is -2. Why? Because it only needs 2 electrons to look like noble gases. And when you add 2 electrons, you end up -2. We can apply the same code of logic to 17 and 15. Where for group 17 to look like a noble gas, we simply need to gain 1 electron. To go from group 15, you need to gain 3 valence electrons. And that tells us their respective charges. With that, we know that group 17's ideal charge is -1. Group 15's ideal charge is -3. It should come as no surprise that in the case of group 18, they're already happy, they're already noble, so they don't have an ideal charge. All right, let's switch things up a bit. Instead of working over here on the far right, let's talk about one on the far left. Let's talk a little bit about beryllium in group 2. Very first element in group 2. All right, let's take a zoomed out picture of it. Let's try to identify the closest noble gases. Technically, beryllium is in the same period as neon. That's pretty good. But if you go one step backwards, in fact, if you go 2, you'll find that the next closest one is actually helium. How do we know that? Look at the atomic number. Beryllium has an atomic number of 4. So put it this way. Beryllium can either lose 2 electrons and it will end up looking like helium, or it can gain 6 electrons. Let me write that a bit differently. Oh no. Or it can gain 6 electrons to look like neon. When given a choice, it's really just a numbers game. It would prefer to lose 2 electrons because it's easier to lose a lesser amount of electrons. For that reason, group 2 is believed to be +2. I encourage you on your own time to make the same logic for the rest. Group 1 is +1. Group 13 is +3. 3 to 12, that's that variable bunch. It's still variable ideal charge. The big question, of course, is group 14. Because see, the issue with group 14, if we take carbon, for instance, its closest noble gases are helium and neon. It has 2 choices. It can either lose 4 electrons, it will look like helium, or it can gain 4 electrons to look like neon. So in terms of our numbers game, it's the same, so there's quite a choice to be made. I'm here today to tell you that group 4 will always lose electrons. So its predicted ideal charge is +4. Before we move on to our next topic of the day, does anyone have any questions? I see a hand, right? If we look at group 13, let me just erase this so it reduces some congestion. If we look, for example, at boron, boron can either lose 3 electrons to look like helium, or it can gain 5 electrons to look like neon. At this point, the numbers game tells us it's easier to lose 3. By losing 3, you become a +3. Any other questions on this? Being able to read and interpret the periodic table is a skill you're going to be continually working on throughout this class. I'm not expecting you to have a complete mastery by the end of today or even by the end of this week. Like I said, this is something we will continually refer to throughout the semester. I see a hand at the front. Okay, so that goes back to thinking about the number of electrons and protons. If we take an example here with the case of boron, boron in its neutral form has 5 protons. We know that protons are positive, so that's 5 plus right there. It also has 5 electrons. We know that each electron is negative, so if we added them together, this is 0 overall. 5 plus added to -5. We can apply that same logic to the case when it loses an electron. You still have 5 protons. However, this time you only have 4 electrons. This means that your overall charge is +1. Same thing for the negative. You still have 5 protons, but now you have 6 electrons. Overall, you're -1. Good question. Anyone else? Okay. The next and last thing we're going to talk about today before jumping into our problem solving session is periodic trends. I mentioned at the beginning of the class how the periodic table is classified and organized such that we see overlapping properties, a pattern of properties, or more specifically, a trend of properties. There are 4 main things we're going to go over: atomic radius. Oh, let's see. Ionic radius, ionization energy, and finally, electron affinity. Let's just quickly define these terms before we jump into their trends. Atomic radius is the size of the atom, specifically in its neutral form. The distance from the nucleus to those valence electrons on those shells. It is the size of the atom overall. Ionic radius takes up the same idea. However, instead of being the size of the neutral atom, it's specifically the size of the ion, whether it be anion or cation. Again, this is measured in distance from the nucleus to whatever the set of valence electrons are. Ionization energy is defined as the energy needed / required to lose an electron. Electron affinity is the energy released when an atom gains electrons. First one I'll be starting with is atomic radius. So just drawing a generic periodic table, not exactly to scale. But enough that we understand the size and the scope. Group numbers to start 1, 2, Well, the sizing is all messed up, but I'll just put 8 over here. Period 1 all the way to period 7. Like I said, not drawn to scale, but just enough so we understand the trend. I see a hand in the front. Yes. Okay. So the thing I want you to understand about atomic radius is that we're really talking about the size of the atom overall from the nucleus to that outermost shell. So if I were to pretend, for example, that my chest is the nucleus and my arm span is the size of this nucleus, what I'm really talking about is how small the molecule is, how small that nucleus is packed tied together, or how large. Going down the group, going down periods 1 to 7, that one's easy. Going down, the atomic radius increases. That intuitively makes sense. Why? Because let's look at the number of electrons. The very first element is hydrogen and 1 electron. And the very last element in this group is francium with 87. Of course, an atom with 87 electrons is going to be bigger than an atom with 1 electron. Going down the group is intuitive. You add more electrons, you add more floors to your building, you get taller, you get bigger. What about across? You see, the challenge here is if we take, for example, something like beryllium, we recognize, okay, beryllium has 4 protons, 4 electrons. We see that, we know that from the atomic number. That's how to read the periodic table. Fluorine, on the other hand, has 9 protons and 9 electrons. So in terms of numbers, yeah, you could make the argument that there are more electrons in fluorine. So in theory, it should be bigger. But remember, they're in the same period. And what are periods? Those are the shells, the rings. In other words, they're on the same floor of the building. So neither one is taller than the other. Sure, they may have more people working on that floor, but it doesn't mean that they're overall higher. Same idea for the size. They're in the same period. This small discrepancy, 4 to 9, is simply not enough for you to say it's bigger. So what happens instead? I talked about how if you pretend my chest is a nucleus and my arms are the rings and they're trying to get smaller, when you have 4 protons and 4 electrons, there is an attraction going on there. 4, they're interacting, 4 of them. So they're hugging each other pretty tight. But when you have 9 electrons, more than twice the amount, 9 protons, 9 electrons, that hug gets so much tighter. In other words, based on the number of electrons over here, their hug is a bit looser. Versus on the right, we're talking that nice classic bear hug. In other words, going from left to right, atomic radius decreases. Let me make this part 1 green too. The decreases one is normally the hardest for people to understand because, again, it comes back to that connection between the protons and the electrons. They're attracted to one another, unlike charges attract, positive and negative. So they're hugging each other tight. 4 protons, 4 electrons, yeah, that's a pretty tight hold, but 9 protons, 9 electrons, that's even tighter hug. We can apply the same logic across the entirety of the periodic table. Next up is ionic radius. Now, of course, the difference between atomic and ionic is thus the atomic is about the neutral atom, that is as found on the periodic table. The ionic radius is specifically when the atom has either gained or lost electrons. Because it varies how many electrons an atom can gain or lose, there is no explicit trend across the periodic table for ionic radius. Meaning I will not be redrawing this table right here and drawing the arrows. Instead, what I will tell you is that cations are smaller than their neutral counterparts. Take, for example, something like lithium. Lithium is in group 1. So it will lose 1 electron. The result will be a cation, Li+, and it will be slightly smaller than the original shell. Shown here, just with scale. Anions, on the other hand, are larger than their neutral counterpart. An example is fluorine. Fluorine is in group 17, so it will gain 1 electron. That will turn into F-. Whatever size it starts off at, it does get bigger upon gaining that electron. The big rule of thumb is the more positive charge, or the more positively charged, the smaller. In other words, we expect something like 5+ to be smaller than 4+ to be smaller than 3+, all of which are smaller than something like -1, -2, and so forth. Next up is ionization energy. This is the energy needed to lose an electron. We know, of course, that atoms can lose electrons, so this, of course, becomes important. Getting back our generic periodic table here, numbers 1, 8, 1, and 7. Again, just loosely drawn to scale. We can think about this logically. Take, for example, group 17. Group 17 is only 1 electron away from looking like royalty. In fact, it only needs to gain 1 electron. So think to yourself, does it really want to lose an electron? No. Losing an electron takes it further away. So it takes a lot of energy to remove an electron in group 17. Take for something, for example, in group 1. Let's look at an actual element. That way it'll help click. Hopefully it'll help click even more. Take, for example, an element like lithium. Lithium is in group 1. It only needs to lose 1 electron, so that way it can look like helium. Its ideal charge is +1. So the Grim Reaper comes calling around for its electrons. Lithium is the first to say, I volunteer. The trend is such that ionization energy increases from left to right. Lithium is a good example to remind ourselves it doesn't take that much energy to lose the electron. versus something over here like fluorine, it really doesn't want to lose an electron. Applying the same logic to going down a group, that ionization energy decreases going down the group. That's ionization energy. Next up is electron affinity. Redrawing our periodic table, putting on our fictitious groups just so we can scale them 1 to 7. Already putting the arrow on so I can get ahead of myself. Let me change that to a different color. Electron affinity is the energy required, the energy released when an electron is gained. Going back to the example we saw earlier, what about fluorine? We already talked about how fluorine only needs to gain 1 electron to look like a noble gas. So it doesn't take that much energy to gain it. Because why? It's like, yeah, I'm happy to do this. All I need is 1 electron and I look like a noble gas. By the same code of logic, lithium, which only needs to lose 1 electron, will not be very happy to gain an electron. It doesn't want to. It'll take a lot of energy. In this way, electron affinity gets smaller, aka decreases, from left to right. Down the group, however, electron affinity gets less predictable, so there is no explicit trend that we can follow. We can make an educated guess, but above all else, it's just less predictable. Do you have any questions? Okay. Any questions? Okay. I'd now like to jump into our problem set. As before, these worksheets remain one of your best practices or question banks when preparing for the exam. This is meant to be an exercise for you to follow along with me, those professor guided walkthroughs. You'll do some questions by yourself. I'll go through them if there's time. And then some questions will be extra credit. The extra credit will apply towards exam 1. You already had 1 set of extra credit last week, measurements and matter. This is our second set. I'm here today to tell you that your extra credit is all of page 4, the last page. All of page 4, the last page. All of problem 10. Oh. Thank you. All of problem, sorry, not all of problem 8. I should say all of problem 9. And on the first page, problems 3 and 5. So I'll reiterate that one more time from the very beginning. The problems assigned as extra credit are problems 3, problems 5, problem 9, problem 10, and all of page 4. would like to specifically start with problem 11. This is on page 3. It's on the bottom half of page 3. This is a question format that I do popularly use in my exams. This table format, that's one of the reasons why the entire back page is extra credit to kind of force you to practice. So we're going to go through a couple rows of this one because while it might look straightforward, there are a couple tricks that you might not, if you're not paying attention to, you're going to miss. Problem 11 states, fill in the blanks where appropriate. The first row has been done for you as an example. And right now I'm going to put on the instructions, round to whole numbers. I apologize for not including that on the document already, but don't worry, if this question is on your exam, it will say, please round your numbers to whole numbers. Okay, so the first row has been done for us. Let's try to understand what the approach was, any tricks we can pick up. All right, the element was boron, the symbol is B, so this will be us reading our periodic table, so I hope we all have it at the ready. Its atomic mass is from the periodic table. Remember, the atomic mass is 10.8. When rounded, it becomes 11. Its atomic number is the number of the element. It's number 5. How do we get number of neutrons? That's that formula. That's going to be mass minus number. That's mass minus atomic number. In this case, you can see that this was 11 minus 5 gives us 6. That's why rounding to whole numbers is so important. Number of electrons theoretically is equal to the atomic number. Remember that they're the same when it's a neutral atom. How do we know it's neutral? Because I did define the charge as being 0 in this row. Please notice on this column of charge, not everything is defined to you as 0. So it is something to pay attention to. So let's go one by one, starting with the first row, sodium. Let's see if you can scan through the periodic table yourself, try to find it. Sodium, one of the tricks you'll have to learn is being able to quickly identify elements on the periodic table. Sodium's atomic symbol is Na. If you couldn't immediately find it based off of the name, do notice what else I give you in the row. I give you the atomic number, which is how the elements are organized, aka sodium is simply number 11. Yes? That's because I've defined the mass for you as it will result in the neutrons. Remember, we talked about isotopes last week. Yeah, so this category right here, number of neutrons, is where the mass will come into play. So this is the kind of table where you need to pay attention to the numbers I give you. Good question. Very good question. The atomic number is 11. That's our most diagnostic tool. Remember, we talked about isotopes, as the student just brought up. Isotopes have different masses, carbon 12, carbon 14. So the atomic number is our best diagnostic tool. It's number 11. The number of neutrons is 24 minus 11. This is 13. All right, let's look at the number of electrons. In theory, the number of electrons is equal to the atomic number if it's neutral. Is this atom neutral? No. I've defined it for you as +2. So if it's 11 electrons normally, and its charge is +2, that means it has 9 electrons right now. So the point of this table is, of course, I will give you some of the cells, and you have to respond in kind. As you notice in this case, the mass of the sodium did not line up with the periodic table. That's because it's an isotope. The charge sometimes differs, and you need to consider that. Let's try the next row, atomic symbol Y. That's all you're given to look for it on the periodic table. Take a scan for yourself. It's just the atomic symbol, the letter Y. All right, hopefully we found it. The letter Y is called yttrium. And its atomic number is 39, which means it's a 39th element. And according to the periodic table, its rounded mass is 89. How do we know when something's an isotope or not? Well, in the case of the yttrium, I did not give you the mass, so you're allowed to assume it's directly based off of the periodic table. In the case of the sodium, I did define the mass. It's on you to recognize this does not line up with the periodic table, hence it's an isotope. Notice I didn't ask you explicitly, however, is this an isotope in the question? The number of neutrons is equal to the atomic mass minus the atomic number. 89 minus 39 is 50. I've told you in this case there are 39 electrons. We know that atomic number is number of protons. We know there are 39 protons. If there is an equal number of protons and electrons, it is neutral. So we would just write 0. I write my zeros with a line through it like that. I'd like for everyone to try copper by themselves right now. It's 12:31. Take about 2 minutes. Answer that row in full, and then we'll go through it together. Take another minute and a half. The bottleneck is finding the element. Once you find the element, it just becomes reading it carefully and correctly. Okay. Hopefully you've all found the answer. Now, remember, in truth, I will never know which cells you answer first. I've been doing it from left to right. But if you spot an answer quicker and you want to fill that in, we can. Why don't we try that right now? Let's try to identify the number of electrons. We know that the atomic number is 29. It's told to us as 29. And we're told that the charge is +5. So how many electrons are present? 24. We did not need to know the identity because that's something that the numbers can help us calculate. Atomic number 29 is copper. Copper is Cu. Careful of writing Co. Co is cobalt. That's another element entirely. And its rounded atomic mass is approximately 64. Do you have any questions on anything from problem 11? Yes. Sure. So in the case of copper or just in general? Okay, so let's try copper. So we know that the atomic number is always going to be equal to the number of protons and the number of electrons, for a neutral atom at least. We're told that it's 29, so it has 29 protons and 29 electrons. Within the same row, we are explicitly told that the charge is +5. Since only electrons can move, 5 electrons are what's moving. They're either being gained or being lost. By losing electrons, that's what makes us positive. So the plus tells us we're losing. The 5 tells us we're losing 5 specifically. 29 minus 5 is 24. I love hearing that. Oh, yeah, I saw your hand. Yes, that was pretty much just a giveaway. Yeah. I saw another hand over here, I think. Yeah. Yes. No, it will not make a difference. Actually, let's just do this row right now so we can clear that up. The student wants us to do the next row that says atomic number 98. She had already identified it to be californium, which is CF. That's in those bottom two rows that we'll largely be ignoring. Californium. Now, on the periodic table, its mass is given in brackets as 251. Just write 251, and that's fine with me. Okay, that's it from problem 11. I would like to do problem 7, just a few of these questions. I would like to do A, C, and K. I'm gonna use a different color because I know I used the blue for the extra credit. A, C, and K. The question asks, how many total electrons do the following elements have as written? Please notice that in some of these structures, they're positively charged or negatively charged. So if no charge is given, it's implied to be neutral. So take, for example, barium, Ba. Look for it on our periodic table. Ba, as in barium, is atomic number 56. As written, it's neutral. So all we're left to say is that it is 56 electrons. PO, take a second to scan for it on your periodic tables. PO is polonium. It's not bottom right corner. Its atomic number is 84. Remember, try to find it on the periodic table. One of the skills is being able to read the periodic table. Polonium is PO, number 84. This charge is 3 minus. So how many electrons does it actually have? 87. Then we have IN. This one might be a little tricky to find. It's kind of somewhere in the middle, congested. Take a second to find it. IN. 49. I guess we found that really quickly. 49 is indium. Let me just confirm. Yes, indium is number 49. It has a charge of 3 plus. Remember, the plus tells us we've lost. 3 tells us we've lost 3. So we actually have 46 electrons. All right, I'd like to do a couple questions from problem 8. A, F, E. All right, because this has to deal with trends, let's just take a second to remind ourselves of the trend. This is asking us, the problem is specifically asking us, I'll read it. For each pair below, circle the one with the larger atomic or ionic radius. So let's remind ourselves of the rules. For atomic radius, as we go from left to right, it gets smaller. If we go down the group, we get larger. When we speak about ionic radius, there isn't an explicit trend. It just depends on the charge. Generally speaking, cations are smaller than their neutral. Anions are larger. The general rule of thumb is the more positively charged, the smaller. Starting off, we have A, CS versus FR. Please try to find those on the periodic table. They'll be very close together. It'll be in the bottom left corner. It'll be in group 1, CS and FR. This is a situation where, as we go from CS to FR, we are going down the group. As we go down the group, we get larger. So which one's larger? Francium. Looking at E as an elephant, we're comparing bromine neutral. We know it's neutral because there is no charge specified. And bromine anion, a negative charge. What do we say about anions? We said that anions are larger than their neutral counterpart. So the bromine minus will be larger. And then finally, in the case of F, we're comparing two ions, sodium plus and Mg2 plus. Technically, neither one is neutral. So what's our big rule of thumb? The more positively charged, the smaller. So Mg2 plus is designated to be smaller. So we expect Na plus to be our answer, that it's larger. Yes. So if it's this one. Yes. So same group. So let's take Apple as an example. Are you asking what if I was comparing CS plus and FR plus? So you're talking, let me just draw this up very quickly. So if I were to ask you to compare these two basically question marks this far apart on the periodic table, and the charges are also different. So let's make a fictitious element. Let's say F minus in the top right corner, and let's say CS plus right here. That comfortable with, is that answering what you kind of confused on? Yeah. In this case, you can use a couple logic. You can go from left to right. You can go down. But one of the big things to remember here is those number of electrons. We've likened these electrons, these shells, to floors of a building. Fluorine minus would have 10 electrons. Cesium plus would have 54. 54 electrons will always be bigger than 10 electrons. So in that case, you would want to use the argument of counting electrons. Yeah. Good question. Anyone else? Okay. For the next couple of minutes, I would like everyone to attempt a couple questions from problem 6. Let's do, I want you all to try to do H, I, and E, so EHI. It's about 12:43. I will go through these questions in the last couple of minutes of class. Take the next like 3 to 4 minutes to attempt it. Sorry? Another packet, yes. You have another packet? Okay. Then you go from left to right. And left to right as it gets smaller. So if you, did you have you writing your notes on this? Oh, I mean, like I was wanting to show atomic radius right here. So we're going across from left to right. So it decreases. So then which one do you say? So what's your answer? And you can't know for sure, right? Because as you just said, we're going down the group. It's difficult to predict. So you could say something like unknown, more tests or more details needed, stuff like that.
Okay, but what's the differences during the same period, right?
Yes.
Okay.
Yeah.
Okay, as a differences.
In about 2 minutes, I'll work through the questions. You are encouraged to collaborate with your classmates, work together. Another 30 seconds. Okay, in the last couple minutes, I'd like to do these questions or at least answer them. Question E asks, which group on the periodic table has the largest ionization energy? Now, of course, you could just refer back to the picture I drew of the trends. You can also logic your way through it. Ionization energy is losing an electron. So a group that has a large ionization energy does not want to lose an electron. Right? Which group definitely doesn't want to lose an electron? It would have to be group 17, the one right by the noble gases. Why? Why would they lose one? All they need is to gain one. So the answer here should be group 17. You could have, of course, also labeled it. Group 17 is called noble gases. So noble gases as an answer also works. Both H and I both relate to iron and copper. So let's take a second to find it on our periodic table. We have iron right here at number 26 and copper at number 29. All right, so they're in the same period. So we're going to go from left to right. That'll be our decider. The first question is, which element has a smaller atomic radius? From left to right, atomic radius decreases. So the smaller one will most likely be copper. You can write the symbol or you can write the full name. That is accepted. Next up, it says between iron and copper, which has a greater electron affinity. Always a good idea just to check the diagram. It says that across a period from left to right, it gets smaller or decreases. So the greater one would be on the left, aka iron Fe. All right, we're going to wrap things up for today. Don't forget, we do have lab tomorrow. Please come dressed appropriately. I will print all of the necessary worksheets for you. You don't need to worry about that. If you have any questions, come talk to me now. If not, I'll see you guys tomorrow. So let me pause the recording.